Alright guys, we're gonna go ahead and get started once the stream is up, so we're good? We're up?
Yep.
Okay, so hey everybody, for all of you guys that don't know me, my name is Michael Benven. I'm the current project manager for the outreach team here on RoboJackets, and today we're gonna have our first TE session, which we're really excited to have. We'll be having our TE sessions every week for the next 5-6 weeks on Saturdays at this time. So with that, we'll get started with Sunny here, who's going to kick off TE sessions for the year. So thank you everyone here that's here, and if anyone's on the stream yet, glad to have you here too. Just keep your questions till the end, I guess, and we'll get started. So thank you very much for coming, and thank you all everyone for being here.
Hi. Just so I can get to know some of you, what teams are you guys from? I think I know Northview is here, right? Titans?
They might be. I think they're showing up a little later.
Okay, so what teams are you guys from?
Well, yeah, 5.
What's that team number? 6705?
6705.
All of you?
Yeah.
Yeah.
Okay, fair. You're from Northview, right?
Yeah.
Okay. What Northview? Everybody else 6705. Okay. I don't really know why any of you are here. I'm sure you guys know how well you did last season, right? This probably isn't like, this is probably just like, you know, it's like, come on, we already know all this stuff. But I'll introduce myself. My name is Sunny Gupta. I'm the lead engineering mentor for 1648 G3 Robotics. I was a student on 1261. I don't know if you know them. They didn't have a great season last year, but they're a pretty okay team. And I spent a little bit of time in Florida. I mentored 5283, not 93. And now I'm back on 1648. Okay. I tend to do everything on my team. So obviously I do robot design and strategy, but then when they need video editing, I help out in that too, business, Neo, anything like that. So we're talking about designing mechanical subsystems, right? Now that in and of itself is a very complicated topic. This presentation that I'm going to try and do in 50 minutes could be broken up into like 10 different presentations, each one of which could be 50 minutes, right? So I'm just going to stick to guidelines, rules of thumbs, things like that, okay? If you have any questions, if you have any details, try and ask them towards the end, right? If you really feel like a passion to interrupt, go for it. But so we're going to start with some basic design guidelines. Now these are things, rules of thumbs that I'm sure you guys have sort of somewhat developed on your own, but these are things that whenever somebody pitches a design to me or whenever they have a recommendation, there are 3 guidelines that I try and measure the recommendations against, right? The first one is make life easy for your drivers. Okay. How many of you are rookies? So this is your this will be your first season coming up. Right? That's great. Right? So what you don't know is that these are drivers from an FRC team. They're standing there. They're looking over the field. The field is 50 feet long, and they can't see half of it, right? Because there's a big airship in the way. So whenever you design anything, you have to think about your drivers. How are they going to use it? How are they going to operate it on the field, right? I see so many designs where people are like, oh, if you put the robot 1.25 inches away from like the scoring platform, it'll go in perfectly. It's like, look, our driver can barely see over the driver station. That's not going to happen, okay? So whenever you design things, you have to make sure they're reliable, you have to make sure they're fast, but you can't put a lot of stress on your drivers. Drivers have to just be able to do it, okay? Next thing is make life easy for your pit crew. So the pit crew is the crew that hangs out in the pit, and their job is to keep the robot up and running. Their job is to keep the robot maintained and functioning for matches. Now, if you design something that's impossible to maintain, if it's impossible to fix, life's going to be hell for your pit crew, okay? So when you put together designs that are really intricate, you have to think about how's it going to get fixed. If this piece breaks, how are they going to fix it at competition? Okay? And actually, there's an interesting story right here. For those of you that were there last year, how many of you remember the robot for G3 Robotics? Yeah, you remember, right? Kind of, yeah. Right? So we had a shooter, we had a ball hopper, we had a gear mech, but what you didn't notice was under all of that was our electronics. Nobody could access anything. So inevitably, when a motor died or when something didn't work, everybody was just like, what's this wire? What does it do in there, right? All of our subsystems were on top of the electronics, and it made life terrible for the pit crew. We almost had something wrong always, And it also made life really difficult for inspections, because inspectors want to be able to trace your wires, want to be able to know where things are going. So multiple times we just had to take the robot apart. We had to pull the top half off so that we could look into the wires and actually see what's going on. Right? So make life easy for your pit crew. Make sure your robots can be easily maintained. The last point is to make life easy for yourself. So if you're, now this is assuming that all of you are somewhat involved in the design process, right? You're going to design the robots, things like that. Don't pick a robot design that you have no idea how to build. Your team has no idea how you're going to make it, right? Because then you're just setting yourself up for 6-10 weeks of just pure agony, okay? So pick designs, pick implementations that you know you can build, that you know are going to be cost effective, that you know are going to be realistic. Now 6705, you guys were really good at that last year because you built a simple robot that was easy to maintain and it worked really well, okay? So keep that up. Okay, now drivetrains, general tips. Now you guys used a pretty good drivetrain last year, that was great, but it has to be reliable. If you can't move, you can't play defense. If you can't play defense, you can't contribute at all, right? So when G3 Robotics actually went to Worlds, our drivetrain just started flaking out on us. So it started dying almost every other match. And that is the biggest red flag in the world. When your drivetrain starts dying, nobody's going to want to touch you. Do you guys know what a do not pick list is? Do some of the veterans know? Yeah. So when you go to the elimination rounds and teams are putting together their alliances, most teams have what's called a do not pick list. So these are teams that, for whatever reason, the team doesn't want to work with them. Having a inconsistent drivetrain is the fastest way to end up on that list. Because if your drivetrain doesn't work, you can't contribute at all. Okay? The second thing is your drivetrain must be competitive. Now that simply means that if you have a drivetrain that's reliable, but it's extremely slow, it's also kind of useless, right? If you have a drivetrain that's reliable, but you can't play defense that well, it's also kind of useless, right? So it has to be reliable, and it has to be robust and competitive, okay? So this is the type of drivetrain that 6705 used last year. It's a simple tank drive. Now there's lots of different variations of tank drive. You have 6-wheel drive, 8-wheel drive, 4-wheel drive with Omni wheels, but it's provided for you in the Catapults, and it's by far the most popular. Okay? Now this is a Mecanum drive. How many of you saw Mecanum drives last year? Yes? What did you think of them? Just
the one that stood out the most was probably Circuit Runners.
yeah.
And their robot was like very fast, and it had Mecanum, so it could go pretty much anywhere very quickly.
Yeah. So Circuit Runners were one of the few teams that actually pulled Mecanum wheels off rather well. Right? Now, if you can't see that little GIF down there, the robot's able to go back and forth, but it's actually also able to strafe, right? So that means that it can go forward, backwards, it can turn, but then it can also do like side to side. Okay? It's a pretty powerful motion. The downside with Mecanum wheels is that they're heavy and they're inefficient, right? So each wheel has to be driven independently. Each wheel costs like $100. So you can imagine if you're putting together 2 robots worth of, Mecanum wheels and things like that, it's going to add up. Right? Now Wheeler always is Mecanum, and they got it right this past season. But I think it's more often than not the teams manage to not get Mecanum wheels right. So this is one topic where I'll be frank, right? My team will never do Mecanum wheels, ever. Ever, right? It's just, they're too inefficient, they're too expensive, they're too much of a headache to figure out. So we will never do Mecanum wheels. Right? But there are instances where they might be a good option. So last year, Wheeler had it figured out, so Mecanum wheels were a good option for them. Does anybody remember the 2015 game? Kind of?
I've heard of this.
Yeah. So it was a game called Recycle Rush, and teams had to stack totes, right? In the past 5 years, it was probably the worst game that First has ever come out with. But with that being said, there was a huge divider down the middle of the field. So there was virtually no defense that year, right? So teams that had Mecanum wheels were objectively better than similar designs with teams who didn't have Mecanum wheels, right? But that's something that I don't think we'll see again anytime soon, right? So Mecanum wheels, They give you omnidirectional motion, right? But outside of that, they're inefficient, they're heavy, they're expensive. So I would recommend, personally, try to stay away from them. Okay. Swerve drives. So I don't know if any of you saw these, but that's what a swerve module looks like, all the way in the corner. What you have is one motor is actually driving the wheel, physically rotating the wheel, and one motor is turning the wheel, right? So what you get is independently driven, independently steered wheel modules. And it lets your robot do crazy stuff like that, right? And there's no loss in efficiency. It's still pretty heavy, and it's very complicated. So that's why if you're going to try and do Swerve, which please, I would recommend against it, but if you're going to try and do Swerve, it's a very powerful drivetrain. So do it in the off season, right? So between now and January, you have 3-4 months. If you're going to try and do Swerve, buy the modules, put them on the Catapults drivetrain or something, and just see how it goes. Okay? But it's a great drivetrain if you can get it working right, and that's a big if for a lot of teams. Okay. Now, which one to use? Did 6705, did you guys use the Catapults drivetrain last year? Yeah, that's a great choice, right? Because it's there, it's free, it works almost all the time, right? And if you're even 1% unsure about whether or not to use it again this year, do it. There's no reason not to. And it's also great because it's pretty modular. So do you guys know do you guys remember 4941, RoboBib?
Yeah.
They're the #1 team in the state, right? State champions, great team. So they use the Catapults drivetrain, but they actually found it was a little too slow for what they wanted. So around week 4, week 5, they ordered up a couple new gearboxes, maybe like $100, and they upgraded their speed by I think about 2 or 3 feet per second, which is not a huge deal. Their drivers adjusted quite quickly, but that's probably the difference between, I don't know, 4 gears and 5 gears, right? So the point is not that you want to go faster, but if you want to use a Catapults drivetrain, it lets you do virtually whatever you want. And Andy Mark is actually pretty quick to adapt to the game. So 2 years ago, a lot of teams wanted to use pneumatic wheels, and there was no really easy way to hook up pneumatic wheels to the Catapults drivetrain. So Andy Mark really quickly put together a kit and said, hey, if you want to use pneumatic wheels, here's what you need. Right? And you just go order it, and bang, you're good to go. Okay? And Catapults drivetrain is also great because it lets you start driving in, about 2 to 3 weeks, depending on how long it takes. Right? Now, there's some people that say that, hey, if all you can do at a competition is show up and drive, then that's great, right? But I don't really agree with that because you get the Catapults drivetrain in the kit, you get the instructions, everything's given to you to drive, right? So every team should be able to show up and drive. Now 6705, Northview, you guys won't struggle to show up and drive. No problem, right? But a lot of teams, for some reason, they try and do complicated drivetrains, they show up and they don't drive, right? If you can't drive, you can't play defense, you can't contribute. Okay? All right, so from drivetrains, we're gonna go to intakes. Now, every game requires some sort of intake mechanism, right? So over the past 5 years, those are the game pieces that first is used. Okay? So you have to intake the object, whether it's a tote, whether it's a recycling can, whatever. And oftentimes there's multiple places to get the object. So you can either get them on the field or you can get them from the human player station, right? Now, like this past year, there's been a trend where getting it from the human player station is just easier, right? So a lot of teams go for it, which is what you guys did. But picking it up off the ground is often just a little faster. It's a little more rewarding, okay? So we're gonna talk about each of those options. So if you're gonna build an intake, 2 guidelines, right? First thing, it has to be consistent. Now, if you were on a team last year, you know that if your intake system jams or something goes wrong, you're done, right? You pretty much have to start playing defense because if your intake system jams, you can't score anymore. So it has to be extremely consistent and it has to be driver friendly, right? Remember, your driver is across the field. They can barely see what's going on. If your driver has to be exactly positioned to pick up your game object, it's not going to work at all. Okay, so it has to be driver friendly and it has to be extremely consistent. So passive intakes are things where nothing actually moves, right? Which is what you guys did last year. So you just drop the gear in and you pull the gear back out, right? But passive intakes can be very deceiving in how simple they are, because you just throw together a simple frame and it kind of works. But the thing is that they're deceptively simple, because if you don't think about every variable, if you don't think about differences in height on the field, you know, the speed of the game object when it's coming in and out, passive intakes won't work, right? So that's why you saw a lot of teams do a lot of variations where, if you look at 1746, they actually have a hinge on their passive intake that like opens up, right? So what that does is pretty much a gear coming out of the human player slot, it almost always went in perfectly into the robot, right? So passive intakes are good because they're passive, they're simple. You don't need motors, you don't need any sort of programming, but you have to test the crap out of them, because you're going to show up on the field and everything will go wrong, right? So if you can test them in your shop and solve all the variables there, then the passive intake will work a lot better when you show up on the field. Okay. Now, active intakes. Active intakes are what they sound like. You essentially have like some sort of rollers or something that pick up the game object off the ground, right? So once again, you have to test very rigorously, and there's a key to active intakes, right? Always use rollers, right? Rollers are essentially just wheels that are on your claw or whatever, and they will go in and they will suck up the game object, right? So if you've been paying attention, why are rollers better than like just a regular claw? Any ideas? Any guesses?
Better grip, more reliable.
Any angle.
Less precision required for the driver.
You were all right, but that is ultimately the point, right? Less precision required for the driver. If you have a claw, the driver can like go up to it and then grab it, but if you have a roller system, the driver can just like ram into it, get it, and then go back, right? The driver doesn't really have to think about closing the claw, the driver doesn't have to think about anything. They can just go in and get it, right? There's an interesting story for that, actually. Anybody know what year that robot's from? So that 1114 in the bottom right corner? It's a while ago, you know? It's from 2008. It's a game called Overdrive. Now that ball that they're holding is 48 inches in diameter, about, right? Which is huge, it's 4 feet. Now, almost every team that year was using some sort of claw, right? So they would pick up the ball into their catapult, and then they would go and then they would shoot it, right? That team managed to package their solution into a roller. So what you see at the very top is a roller that pulls it into that little claw-like mechanism, right? And in my opinion, that was the difference for them. That was what allowed them to dominate and essentially not lose a single event that year, right? They won 3 regionals, they won worlds. So you almost always want to have a roller solution if you're picking up off the ground, always. And if you're in one of those games where it's challenging to come up with a roller solution, like 2008, if you can come up with the roller solution, then that might be the difference that puts you above all other teams, right? Especially in our district. Now, shooters. So over the past 5 years, these are the different game objects that have been shot in FRC, right? Obviously, you guys are familiar with the fuel from this year. The boulders were 2 years ago. That ball that you see is actually a little smaller. I think it's about 2 or 3 feet in diameter. That was used in 2014. And the Frisbees were used in 2013, right? I don't know if you guys ever seen these robots around at demos, things like that. But essentially, the goal is the same. You pick up the ball and you have to shoot it somewhere. And when you're dealing with large game objects, catapults are kind of people's go-to, right? So, yeah, catapults are people's go-to. The trick with catapults is often just keeping the ball secure in the cradle, right? So that robot the way it's set up, the ball might not be terribly secure in the cradle. So that means that if they get hit from the side or something, there's a potential for them to fire a shot off wrong, or the potential to actually lose the ball. Right? But if you actually design a catapult, there's two ways to go about it. The first one is pneumatics. Now this is getting into a little bit of detail, but if you just hook up your basic, like a single pneumatic cylinder, and you hook it up like that, chances are that it'll give you that shot, but it won't be very, very powerful. Right? There's two things you need. First thing is strength, so that means adding more and beefier pneumatic cylinders. And the second thing is a high flow rate, right? How many of you are familiar with pneumatics? Nobody, great. So pneumatics essentially have a cylinder, which is this puppy right here, right? And the second thing you have is a solenoid. The solenoid is what's physically pushing the air into and out of the cylinder, right? In order to get a good pop from the cylinder to actually shoot a ball, you need to have a very, very high flow rate solenoid. Right? So these can be kind of expensive. So this is something to keep in mind, but if you can get a pneumatic catapult working, especially working well, you don't have to worry about tuning it, you don't have to worry about, you know, making sure that the bands are the right strength or whatever. Once this system's working, it's working. And so that's why this is kind of like the ideal solution in my mind. Right? But people also love to go the whole like tension and then the release. So what you need is, you need essentially a catapult that has tension on it. So in this one, the tensioning bands are right here, and the catapult's actually in its firing position. And you need something that'll pull the catapult down, right? But it's not enough to just simply drive your motor backward and let that thing fire. You need something to actually like physically release that pressure. So that's why you need a mechanical release. So there are lots of ways to do mechanical releases, right? The best / most consistent one in my mind is the shifting gearbox. Right? Now you'll have to do some playing around depending on the force, because if it's an extremely high force, then you'll need to reinforce the gearbox. You'll need to make sure that it shifts stronger. But that's another option. Okay. Finally, a wheeled shooter design. Now you guys have, hopefully some of you guys saw this last year, but this shooter type has a lot of variables, and that's probably the hardest part about creating a shooter like this, is that, you know, you have the wheel type, you have the compression, you have the flyweight, you have the motors. What combination of those are going to work for your game object? Right? And the only way to really figure that out is prototype, right? Prototype, prototype, prototype. So if you're looking at the wheel type and the compression, right, softer wheels are very grippy, but they tend to wear quite a bit, right? Harder wheels don't grip as much, but then they won't wear as much either, right? So in this year, this was 2013 with the Frisbees, the pneumatic wheels up against the kind of rigid, you know, Frisbee, those wheels gripped the Frisbee really well, and they shot amazingly, right? For some reason, my team did not opt to go that route, but a lot of teams that did have Frisbees went with the pneumatic wheels. Okay. And compression is just one of those things, you have to play with it, right? Because if the compression's too high, you'll actually slow down the wheel too much, and your shot won't be good. If it's too low, your wheel won't catch the game object, and your shot won't be good either, right? So these are just guidelines. The thing is that you have to play with it. Like my team last year, we spent, I think, 2 weeks just playing with different wheel types, playing with the compression, things like that, to figure out what's going to work for us. Okay. And now flywheels and motors. So this year, you guys probably got a chance to see some teams that shot like a ton of balls, right? And for you rookies, last year teams had to shoot wiffle balls as well as score gears, right? And so there were some teams that could just absolutely shoot at an insane rate. We're talking like maybe 5-10 balls per second, right? And the way they do that is that they balance a flywheel weight which lets you keep the speed of the shooter wheel up with the motors, which actually provides the power for, power for keeping the shooter speed. So, but the balance part comes in that if your flywheel weight is too high, then it's going to take forever for your shooter to come up to speed, right? But if you have too many motors, your motor, like your shooter system, will take too much power away from the rest of the robot. So the balance comes in that you want to have a shooter that spins up quickly, that can maintain speed, but you don't want to take power and just kill the rest of your robot. Right? And this is also something that comes with a little bit of prototyping and a little bit of experience. But you have to do what you're going to do and see how it goes. Right? All right, climbers. So climbing is a pretty commonly used end game tactic, right? So for those of you who are new, the end game is like the last 30 seconds of a match, right? So that's like usually when the core game dynamic kind of stops or pauses and teams shift into like climbing or things like that. Now, these are the things that teams have had to climb over the past 5 years. That is a big pyramid. The image on the far right is just a tower from 2016, and of course you guys had the airships last year, right? First step for climbing is grabbing, right? This is typically the hardest part of the challenge because usually the bar is very high. So you have to come up with an arm or something that'll reach up and grab the bar, and then you have to pull yourself up. But the thing that kind of broke the challenge last year was Velcro, because you could just use Velcro, grab onto the rope, and you're going up, right? But in previous years, it wasn't that easy. So, assuming in the future that the climbing challenges will be somewhere in the middle, they won't be as easy as last year, but they might not be as difficult as previous years, you're going to want to make sure that you can grab onto the climbing rung or whatever very easily, right? And it just goes back to your drivers, that you want to take pressure off them, but also you don't want to take that long to grab on. Okay? I'll talk about this in the next slide. So if you're looking at the GIF, that's Team 254 out of California. You notice how they climb that thing in about 6 seconds, right? You have to understand, right? Most teams could not even make that climb, right? My team that year, we could get onto the first rung maybe, right? These guys are just like, bam, we're up. So it's pretty incredible. Now the point here is you have to climb in a reasonable amount of time if you're going to try to climb, right? Don't be one of those teams that takes like, you have a 30-second end game, it takes them 25 seconds to climb, right? Because A, that's kind of annoying, because if they miss their window to climb, then they're just stuck halfway up, you're like, oh, I could have gotten the points. But B, I'm sure you guys noticed that in the end game, there's like a lot of rushing around. So, teams are almost like the big bonus, or like, as teams go to climb, there's like less robots on the field. So like you have a little bit more room to maneuver around, like maybe score some extra points. So you don't want to be one of those teams that just takes yourself out of the game right at the 30-second mark, right? You want to be able to maybe go get one more game piece and score it. So that's why climbing quickly is, I'd say it's pretty important. Now, if I had to put like a rule of thumb, right? Now, this was a pretty difficult climbing challenge. Right? Last year, did like you guys have like a time that you were aiming for, like how quickly you wanted to be able to climb?
Not really.
Not really. So last year, I think our team was like we wanted to be able to climb in about 5 seconds, right? So 5 seconds to grab the rope, right? Grab, and then another 5 to climb. So that means that we wanted to be able to execute our climb in under 10 seconds, right? Which I think is a fair rule of thumb. Okay. Now this challenge specifically was very hard. You had teams that could go to the top, but they needed to start right at the 30-second mark, right? And you had teams that went up every which way. Some teams went up like these guys. Some teams like shimmied up the side of the pyramid. It was a pretty crazy year. So. But when you go to balance your motor usage and pretty much figure out what's going to get you your climb at your right time, there's a spreadsheet out in the internet. It's called JVN's Design Calculator. Right? and it's actually maintained by Vex. And you can essentially just put in all your variables, like, hey, my robot weighs 100 pounds, I want to use these motors in this gear ratio, and it'll say, okay, yeah, it should climb in about 5 seconds. And so then you can play with those variables and say, okay, if I use 2 of these motors, how fast? Say, oh, you can climb in 3 seconds. Right? So on my team especially, this is a very useful tool. Right? Nothing gets built, nothing gets prototyped unless it's been through this calculator so that we know we have an expectation of its performance. Okay? So if you're going to be building a climber in the future and you're picking out motors or something like that, honestly, if you're building anything in the future, you want to use JVN's design calculator to just proof your decisions. Okay. Finally, is staying up. Now, did you guys use a wrench to stay up like everybody else, right? So there were some teams last year that didn't stay up, right? And it's kind of weird because like they went up and then they hit the touchpad, and then as soon as the game ended, they fell back down. Like not hard, but they fell. You can kind of do that as long as you don't damage the robot. And obviously, you know, stalling motors is never good, right? So if you're going to climb, use a ratchet, use a wrench. These are very common things that teams use to not backdrive, to not fall. Okay? These things are like $2 at Home Depot. There's like no reason not to have one of these things. Okay. Okay. Summary. So Drivetrain has to be reliable, and if there's any doubt, use the Catapults. Intake has to be thoroughly tested, and it has to be very driver friendly. Your shooter, you have to prototype. You have to prototype every single thing without your shooter, because that's how you're going to get it to be the most consistent. Okay? And your climbers, grab quickly, climb quickly. Okay? And that's the basics of how to design a mechanical subsystem. Right? Now, each one of these things can be broken down into their own presentation, because you know there's 20 years of FRC to go look at, and there's a ton of really good drivetrains, intake, shooters, and climbers. Right? So 67 and 5, you guys are in your 2nd year this year. Right? There's a saying in first that's like become really common now. It's that nothing is new, right? Which is a pretty common saying in general. But the games, while the games themselves don't really get recycled, the challenges kind of do, right? So if you find yourselves wondering like, how do we do this? Chances are, a few years ago, a very similar challenge was offered to the teams, and a few teams came up with some good solutions, right? So always worth a good look and research. So with that, that's the end of my presentation. Not that painful, hopefully. Are there any questions about anything? About the guidelines, about suggestions, any comments, anything like that? Any questions online?
Nope.
Are you guys going to grits?
Yes.
Are you guys going to let your rookies drive?
No.
What? Why not?
Yes.
Maybe. We undecided.
So our rookies, so I'm on G3, right? Our rookies are actually building a robot for grits, and they will be driving it. So we're going to be terrible. No. We'll probably do fine. But I would encourage you, like your team is more than half rookie, right?
Yeah. I think we're looking at making an active gear intake, and then letting newer people use work on that and stuff. So
yeah, so that'd be good. It's typically what we do is we let in the past when we don't build an entirely new robot, we would let rookies drive in the qualification rounds. So this year you'll get at least 10 qualification matches. We would let rookies drive in the qualification rounds, and then we would let the actual drive team take over in the eliminations. Right? Now it creates kind of a staggered system because your team may not do that well in the qualification rounds, but then you get on a stacked alliance in the elimination rounds, and you have your regular drive team in there, and they're kicking ass. So it's
we have an extra tournament we're going to.
Oh yeah, but
We don't know yet.
We don't know yet.
We hope it's
we can-
We're gonna just try to go to 3 this year, do the extra qualifier.
Oh, you guys are talking about in the season?
In the
Yeah.
season,
Yeah.
so we'll be able to, use that as training as well.
Oh, that's great, that's great. So which ones are you guys planning on going to? Have you picked them out?
Gainesville's our first choice. Metro Atlanta also, because that's way closer than any of the others. But that
Duluth?
is it in Duluth?
Duluth.
Yeah.
Okay, yeah. And then Dalton, right? So, yeah.
We'd like to go Gainesville, Dalton, and then do the Metro Atlanta, which is the last week, is just our third, it doesn't count toward points.
Yeah, that's a good idea.
We'll see.
That's great. Okay.
And then Columbus would be our other choice if we
Yeah.
don't get one of those.
Yeah, we were going to try and do that as well.
Yeah.
I think if that last one had come inside the perimeter, so I think they were planning on doing that like Woodward.
Yes.
So if they had moved it there, then it would have been great because like we don't have to pay for hotels or anything. So interesting. Okay.
We would not have to. So.
Couple questions from the internet.
Sure.
How do you take your mechanical parts and make sure that they work with your electrical parts?
Okay. Who asked that?
That's from Ben.
Oh, right.
I think there's another group over there now.
Yeah. Okay. So how do you take your mechanical parts and make sure they work with your electrical parts? A lot of that is just people generally don't. Right? I'll be frank with you. So the way we do it on G3 Robotics is just kind of, it's probably not very good. It's that we design mechanically as much as we can, and it's kind of up to the electrical team to kind of keep up with what's happening, right? So that team is responsible for making sure that the robot works at the end of the season. Right? So that means that they need to know how many motor controllers they have. They need to know what kind of sensors they're going to need, right? But the thing is, that's not a great system because then you have the electrical panel mounted under all the other subsystems, right? Ultimately, I think it comes down to a part of design that if you have a shooter, you're gonna want to have encoders or vision sensors to watch the shooter speed. And as a designer, I think you have two responsibilities. One, integrate those sensors cleanly, so make sure those sensors have mounts, make sure the sensors aren't gonna get ripped off every time you run the robot. And two, make sure that your controls team, the programming and electrical team, know that they're gonna have to be working with these sensors. So that come week 2 or week 3, they're already practicing with encoders. They're already practicing with like light sensors. Okay. Anything else?
Yeah. So, what are some things you can look for when you're debugging mechanical components?
If something like snaps in half, it's probably not
Like
working very well. So that's a pretty generic question, right?
Yeah.
And I think it kind of depends on the subsystem. So I'll just really quickly run through the subsystems. So like drivetrains, right? What are the things you're looking for? You're looking for making sure that the two sides of the drivetrains are running at approximately the same speed. And B, you're looking for weird noises, right? Because if motors start getting jammed and things like that, they're going to complain. They're going to complain very audibly. Okay? Intakes, if you're looking for some sort of issues, like something's wrong, you want to almost specifically look for jams, right? So it's actually very interesting because whenever you see teams testing their intakes online, they put the robot down in one place and they feed the feed the robot in like the same place over and over again, right? It's like that's great that it works in that one configuration, but on the field, the ball's going to come from every which way. So you want to keep an eye out for jams, for intakes. For shooters, I just think the biggest thing is if you have a shooter that's working, the biggest thing that something is going wrong is variances. Right? So if you're shooting at the goal and you notice that the ball is like overshooting, right? Well, it means there's probably something wrong with maybe the programming, right? Or if you're aiming for the goal and the ball just completely like overshoots, right? Then maybe there's something wrong with the sensor. There's like something not working there, right? And climbers, if your robot falls, you know there's something wrong, right? We actually had that happen. We, like the robot was going up, and it got about halfway up, and then it fell to the ground, and then it went back up, and it got up. So we actually figured out that what happened there was that the rope slipped for some reason, and it fell like that. The biggest thing, I think, is watch the performance of your robots, watch the performance of your systems, and be your own worst critic, right? Because if you're critical about how something's working, you have probably noticed that something's wrong, you've like noticed a bug, and if you go and try and find it, you'll like actually get the root cause. Anything else?
What's something you can look for in a game to decide whether an active or passive intake might be better to build?
Active or passive intake might be better. So here is the thing. An active intake, if built right, will always be more competitive than a passive intake that's built right. And you can just kind of see it in the game progression this year. So take, for example, 4188 Columbus Space Program, right? They started off with a passive intake, but as the game progressed, they actually moved to an active intake, right? And some teams started off fully passive, but then they moved to a hybrid, right? So I would say if you're in a game and you're looking at active versus passive, right? I would start with passive, simply so that you can understand the game, understand the dynamic, and maybe have something to play with in week one. And especially if you're going to Gainesville, you're going to week one, right? But then, as the game gets more competitive, an active intake is almost always going to be the better option, right? But you're going to need time to implement it. You're going to need time to understand how the game works. So specifically, like, how do you tell whether it's passive versus active? The solution is always active. The question is, you know, do you have time to implement it? Do you have the resources to implement an active solution? Anything else?
Yeah, that's it.
Okay. So thanks for coming out. I'll give 2 shameless plugs. One, for the mentors who might be listening or watching, we have a mentor Slack for mentors across the district. If you're not in that and you would like to be, let me know or let anybody know, and we'll get you added. Second thing, next week, Kellen Hill from 1746 will be here. He will go into more specifically the strategies around picking what you're going to do, right? So if last year you built every single one of these things, that's great, right? But very few teams actually did. He will go into the strategies around, okay, how do you pick whether you're going to do a drivetrain and a shooter, or a drivetrain and an intake and a climber. Right? So he'll go into more details about picking what's best for the game. Yeah.
Thank you. Thank you very much for presenting and starting off TE sessions. That was really awesome. I'm sure a lot of rookies, and especially all the rookies here, really appreciated it because there's a lot of good information there and it starts generating ideas before season even begins. So thank you very much for that. You had some words?
Yeah, so this will be saved, also be saved to our YouTube channel. So if anyone wants to go back and read through or watch some of the things that you covered, it'll be on our YouTube channel as you continue to watch it. Yeah, thank you very much.
Alright, so with that, I guess questions are over. So thanks everyone for coming. And that's it for our first TE session. So thank you again.